Hello, students. All right, ladies and gentlemen, we are going to continue this topic where we left off yesterday. And you may recall that yesterday I posed a question to you at the end of the period. How is heat measured? And we had a little discussion about that. And one of the words that came up was this word temperature. And so that's where I'd like to pick up our discussion today. Temperature. Temperature measures the average kinetic energy, otherwise known as the energy of motion, of molecules. Now, this ties in a few words that we've gone over before. Average kinetic energy. We learned about kinetic energy in our last unit. Energy of motion. And in this context, we're talking about kinetic energy on a molecular level. So if we could put on our magical glasses and look at the inside of a substance and see the individual molecules moving around, then we would be able to see the temperature of a different substance, because we would be able to see the movement of molecules. The diagram on the left compared to the diagram on the right have arrows of different lengths. In this diagram, the longer the arrows, that represents a faster average speed or a greater average kinetic energy. So which one of these two illustrations do you think would be hotter? Hopefully you said the one on the right, because it has a greater average kinetic energy or energy of motion. When you've got particles moving around faster, that's a measure of something that is going to have more heat energy. And when we measure that temperature, it's going to be hotter. Now, speaking of measuring temperature, anyone tell me, what tool do we use to measure temperature? Hopefully you answered a thermometer or a thermometer. In fact, literally, the word thermometer is made out of two parts. Therm, does anyone know what the prefix therm means? Heat. And meter, the suffix meter, what does that refer to? Measurement. So thermometer or thermometer, the word literally means heat measurement, and it is an instrument used to measure temperature. Now, yesterday I showed you kind of a cool little device here, a little hand boiler that I had some fun with, showing how hot I am. And I want to show it to you again by holding on to the bulb with all of the liquid. And I want you to watch what it does to that liquid. Woo! Forces the liquid to the other ball and makes it appear as though it is boiling, thus the name hand boiler. We'll make it go back the other way again so you can see it. Wow, look at that fountain of hot liquid just coursing through the tube. Well, guess what? This is kind of a crude form of a thermometer. If you look at the diagram behind me, you notice that this diagram is a hollow tube with a red liquid in the bottom. This also is a hollow tube with a red liquid in the bottom. Right now, I'm not adding any heat energy to it, but when I hold on to the bulb, look what happens to the liquid. It goes up the tube higher and higher and higher until it eventually, if it's hot enough, will enter the top tube. And it's getting closer. It's getting closer. I'm pretty hot. Let's see if it enters the top tube. And there we go. Check it out. So by my adding my body's heat energy to this red liquid, it's causing the liquid to go in the only direction it can, up the tube. Likewise with a thermometer. This hollow tube thermometer, if you add heat energy, it's going to cause the internal motion of these molecules to move faster, and there's only one place for them to go, and that is up the tube. And so that is how a thermometer works to measure temperature of different substances. And we'll be using thermometers in the lab this week for our lab activity. But I want you to be aware of the fact that not all thermometers are the same. There are different kinds of thermometers because there are different what are called temperature scales. And we're going to be talking today about these 3 different temperature scales. And for some reason, as I begin this, I have a hankering for some fried chicken for some reason. I could go for some KFC here today. But we're going to be talking about the 3 temperature scales, and we're going to begin with the one that is probably the most familiar to you. But it is the one that we're not going to use in the lab. But I got to talk about it because you are familiar with it, and there's an interesting history that goes along with it. And that is the Fahrenheit scale. The Fahrenheit scale is named after this dude, Daniel Fahrenheit, who lived in the late 1600s, early 1700s, and was interested in doing experiments with heat energy. And until his time, you couldn't just go down to the local hardware store and buy a thermometer to do an experiment with. So he kind of created his own thermometer. He knew a glass blower in town who blew a tube out of glass, a hollow tube, similar to the ones that we're familiar with today. And he filled the bulb of it with mercury, a liquid metal. Again, we don't use mercury thermometers. We use thermometers with another red liquid in it. And by the way, mercury is a silver liquid. It is one of the only, actually, it's the only metal that is a liquid at room temperature. There are other metals that can be turned to liquids at relatively low temperatures, but most metals are solids at room temperature, except for mercury. Mercury is a liquid. Well, Fahrenheit was aware of the cool properties of mercury, and so he used that in his thermometer. But let me tell you a little story about Fahrenheit. As I said, he was interested in quantifying or measuring with numbers changes in heat energy. And so he developed this thermometer, but since he was the first one to develop it, there were no numbers on his thermometer. It was blank. And so he wanted to think of something that was really cold and really hot to base his thermometer and the measurements on. Now, keep in mind the time frame that he lived in, late 1600s, early 1700s. There were no freezers that existed back then. What can you think of? Can you think of anything that is found in nature that could provide someone, a scientist like Fahrenheit, something that is really, really cold? Have any of you ever made homemade ice cream? If so, pause me now and talk about how you make homemade ice cream. All right, well, I think Fahrenheit knew that mixing ice and salt together lowered the temperature dramatically and made it super cold, so cold that you could get frostbite. So be careful if you're ever experimenting with ice and salt. But here's the deal. Fahrenheit, and by the way, I'm going to take a little artistic liberty here just to describe what Fahrenheit did, just to make a point. So Fahrenheit got together a bowl and put some crushed ice into it, mixed it with salt, He took his tube with his liquid mercury in it, put it into this bowl, and he watched the liquid go, and then it stopped. It stopped at a point that he determined was the coldest temperature he could produce in his little laboratory, and so he drew a line. And next to his line, he labeled that line with a number. Do any of you have a guess as to what that number was? Well, that number was a 0. 0 degrees Fahrenheit is the temperature of an ice-salt mixture. In fact, it is 32 degrees below the freezing point of water in the Fahrenheit scale. And who could tell me what the freezing point of water is in the Fahrenheit scale? 32 degrees Fahrenheit. But he labeled his line 0, 32 degrees below the freezing point of water. Now, working with this cold stuff made his hands cold. Now, have any of you had cold hands in the wintertime? What do you do with your hands to get them warm? Maybe some of you rub them together, but the best thing to do with your hands to get them warm, don't run them under warm water. That could be dangerous. You take your hands and you put them under your armpits. That's the best thing to do to warm up your hands, by the way, because that's body temperature. Well, Fahrenheit's hands got pretty cold. And so he put his hands under his pits and realized that, hey, I'm pretty hot. So he took his thermometer and shoved it up his pit and watched the liquid mercury. And he saw the liquid mercury go boo, 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 boo. It went up really far and then it stopped. And so he drew a line where it stopped and he wrote a number next to that line. What number do you think he wrote next to that number? No, it wasn't 98.6. That would be a silly number for him to write. He wrote the number 100. After all, 0 to 100, that's a nice scale if you're developing a scale from scratch. 0 and 100 are good numbers to use. So why did Fahrenheit use 100? Well, it turns out the glass blower that he used, it was a little bit irregular. It wasn't a perfect thermometer, and he may have been running a fever the day of his experiment. So for the last 300 years, we've been basing the Fahrenheit scale on Danny Fahrenheit's body temperature while running a fever and using an improperly produced glass tube. It was an imperfect measurement. That's why body temperature today is 98.6 degrees Fahrenheit. It's because we know after lots of experimentation that Fahrenheit's thermometer wasn't exactly accurate. If it was, normal human body temperature today would be 100 degrees Fahrenheit. So when you're getting off the bus every day and they take your temperature to make sure you're not running a fever, it should have been 100 degrees would have been a normal body temperature. But because of the history of Danny Fahrenheit's experiment, it is 98.6 degrees and not 100. Be that as it may, the Fahrenheit scale based on an ice-salt mixture and body temperature. And the reason I told this story is because, you know what? Body temperature, not a good thing to base a scale of measurement on because, hey, we're all different and our temperatures fluctuate a little bit. And there was somebody else who came on the scene who pretty much realized this. And it was around the time that the metric system was being developed. You may remember the metric system being developed and how they wanted to get rid of using body parts to make measurements with. And so under Celsius, this dude came around and developed around the similar time as Fahrenheit, but he developed what we today call the Celsius scale. But back in his day, when he invented it, he didn't call it after himself. He wasn't egotistical like that. He actually called it the centigrade scale, and you'll see why in a moment. In fact, it wasn't until I think 1948 that the centigrade scale was called the Celsius scale, named after this scientist, Anders Celsius. But here's what Celsius did. Celsius took a similar thermometer, hollow tube with mercury inside. His was a little bit better produced than Fahrenheit's, however. And he wanted to base the measurement of temperature on standards that wouldn't change. And you may recall that in our discussions of the metric system and how beautiful the metric system is based on standards that would not change, or at least in that time frame and in that understanding were logical things to use. And water is a great standard, and it was used in the metric system, and it was used by Mr. Celsius as he developed his measurement system for measuring temperature. So when he took his thermometer, he based it on the freezing point of water and the boiling point of water. Doing his experiments in the lab, he was able to pinpoint that temperature at which water freezes. And in degrees Celsius, do any of you know what that temperature is? When water freezes into ice, goes from a liquid to a solid, what temperature is that? Well, it's 0 degrees Celsius, a logical, easy number as your starting point. Then he took that water, and instead of freezing it, he started heating it up. And at the point that the water started to boil, he drew another line and he recorded that as the boiling point of water. And do any of you know what the boiling point of water is in degrees Celsius? 100 degrees Celsius. So 0, 100. Now, you got to give it to Fahrenheit. He used 0 and 100 as well because he thought it would be easy. And it is easy in science to make measurements based on 0 and 100, and easy to make a ruler, a graded scale based on 0 and 100. It's just his system was based on something other than water. But in fact, in the Fahrenheit scale, do any of you know what the boiling point of water is? It's 212 degrees Fahrenheit. Again, metric system, degrees Celsius, formerly known as centigrade. Centi meaning 100th of something. The centigrade scale, now known as the Celsius scale, was measured in 100ths of the distance from 0 to 100, the freezing and boiling points of water. So a little interesting history about the Celsius scale. It is the Celsius scale, also known as the centigrade scale, depending upon where you are in the world, still called the centigrade, which is logical if you think about it. This is the scale that we use in science class because it's based on the standard of water. But there is one more scale that you need to be familiar with, and it is the Kelvin scale. In fact, we will be using the Kelvin scale for certain things too. We just don't have a Kelvin thermometer that we're going to be using because the Kelvin scale is based on something called absolute 0. Now, this is a theoretical temperature that is measured mathematically. We haven't been able to completely achieve absolute zero yet, although we've gotten pretty close to it. Absolute zero is the point at which all molecular motion stops. And Lord Kelvin, or William Thomson, our scientist of the week, he was talking about absolute zero before it was cool. Okay, so the point at which all molecular motion stops, if that were to happen in the universe would be completely frozen solid. This is not a temperature that we want to strive for in the universe. However, I will just mention now, we'll talk more about this later in the year, that scientists are looking for substances called superconductors. Remember, yesterday we talked about substances that are conductors. They conduct heat energy. Well, in our modern age here, where we rely on computer technology, scientists are feverishly looking for substances that are superconductors that can allow electricity to flow without any friction at all. And if you think about last unit, when we talked about friction being an enemy of efficiency, the less friction there is, the more efficient it is, the machine. Likewise, in the electrical world, if you could produce a computer that uses superconductors where there is zero electrical friction, you could have computers that are so much faster and so much smaller than the ones that we have even now. It will boggle your mind. They might actually compete with the computing power of the human brain, which is pretty outrageous when you think about it. So Lord Kelvin, he was doing experimentations at extreme temperatures, extremely low temperatures. And so all he did was use the centigrade scale, now known as the Celsius scale, and based on that scale, he calculated at what temperature all molecular motion would stop, or the point at which there would be zero kinetic energy. And he calculated it to be about 273.15 degrees below zero Celsius. Now, we've been tweaking that number with recent experimentation. We'll talk about that later on. Just know for now, it's really cold, much colder than 0 degrees Celsius. So, as we continue our discussion of these different temperature scales, let me just give you a comparison of some common temperatures for us to finish up with here today. The Fahrenheit scale, that's the one that you're most familiar with, likely. The freezing point of water, 32 degrees Fahrenheit. Body temperature, 98.6 degrees Fahrenheit, and the boiling point of water, 212 degrees Fahrenheit. But as I said, we're not going to use the Fahrenheit scale after today, certainly not in the laboratory in science. We use the Celsius scale. And the Celsius scale is all the way over on the left-hand side here. And again, the boiling point of water is 100 degrees Celsius. Body temperature, 37. And the freezing point of water, 0 degrees Celsius. And I'm just rounding to the nearest whole number here. Absolute zero in the Celsius scale, we can just say 273 degrees below zero. Because 0 degrees Kelvin is absolute zero, which is what the Kelvin scale is based on. And you can see that that's minus 460 degrees in the Fahrenheit scale. So the Kelvin scale, the third scale here, based on 0 degrees Kelvin, absolute zero, and the temperatures increase from there. By the way, you didn't hear this from me, but if ever you wanted to pretend that you were sick so you didn't have to go to school? Simply get a thermometer that's measured in the Kelvin scale. Get a Kelvin thermometer, because even if you are completely healthy and you take your temperature in the Kelvin scale is going to be 310 degrees. That's body temperature in the Kelvin scale. So if somebody at home takes your temperature and you're in bed and you've got a Kelvin thermometer, they're going to look at that and say, there's no way you're going to school today. We got to take you to the hospital because your temperature is sky high, 310 degrees. I'm surprised you're not dead, kid. So on second thought, you may not want to use that as a ploy to get out of going to school. But here we are again, the comparison of the different temperature scales, Fahrenheit, Kelvin, and Celsius. Make sure you have these written down in your books. And I'll tell you what, we are going to call it quits for today. And tomorrow, we're going to talk about a unit of heat. For today, I'm going to say for now, bye-bye.